The last thing I want to do is have people unlearn something, but the reality is that's kind of where we're at today. So if we think back to Bohr theory, which would have been the model of the atom that we learned in grade 11 chemistry, probably even before that, where the atom looked like a nucleus in the middle and then these circular orbits going around it, and I know that looks more complicated than what you probably remember, but we'll get to that in a minute, where the atom had these specific energy levels. So the orbits were energy levels, and they were circular, and then if you added energy to the atom, the electron was going to absorb that energy, move to a higher energy level, and then it was going to fall back down, and when it fell back down, it released energy in the form of light, and that's kind of what all these lines in the middle mean. Now, a lot of that stuff still remains in terms of the energy going in and that going to the electron, and when the electron goes to a lower energy level, energy comes out. But it gets a little bit more complicated than just simply these rings, and that leads us to quantum theory, which is the currently accepted model of the atom, and it does a much better job of answering questions, but it doesn't answer all the questions. So whether or not this becomes the last word, I shouldn't point to me, this becomes the last word in atomic theory, I don't really know, I can't really tell you, but it is the currently accepted model of the atom. Now, one of the problems with Bohr theory was that there were certain implications or certain, if you looked at the theory in a little bit more detail, then that model meant these things. So for example, higher energy levels, you had to have the electron moving faster. Well, that kind of made sense, because how does speed look like in a particle? Or how does energy look in a particle of the same mass? You need more energy, you got to go faster. Then you also should have been able to calculate exactly where the electron was, not maybe where it is on that ring, but which ring it's on, and therefore how fast it's moving. And then that also meant that we should be able to calculate the radius of that circular orbit based on all of those other factors. And that ran us into a bunch of problems. And Bohr kind of admitted that, and we ran into that problem right away with Bohr theory, was that he could explain how many electrons could fit into each orbital, but he couldn't tell you how they got there or when they went there. And that was not a huge problem for us because we limited how much we used it, but it ended up being a problem with Bohr theory. Probably the main problem with Bohr theory is that it works really, really well for hydrogen and only for hydrogen. So out of 118 atoms that we have on the periodic table right now, it works super well for one, so not bad. So that leads us to quantum theory, and quantum theory replaced Bohr theory fairly quickly in the whole timeline of atomic theory and understanding. And as I mentioned before, it is a currently accepted model. It uses a concept called wave-particle duality, which basically means that small particles like electrons show wave-like behavior, which means the normal physics rules that we would have applied to Bohr theory or to particles don't actually apply when you're dealing with small particles that can have wave-like behavior. Now, we're not going to get into all the physics behind it. I recommend you take physics for that. What we are going to do is note that it's a mathematical model. We're not going to do the math, so we don't need to worry about that, but it is mathematical, which means it's hard to draw a picture of, so we end up describing it in more numerical terms rather than visual terms. So if we look at some of the structural parts of it, we end up with something called the Heisenberg uncertainty principle. And that states that you cannot know the position and the speed of the electron, which is one of the things that Bohr theory said you should be able to do. You can predict where you are likely to find an electron. So we end up talking about probabilities. And then once we end up with these different possibilities for where the electron might be, we end up with this probability distribution that we refer to as an orbital. Not an orbit, an orbital. And they're not circular. That's one thing that we're going to have to get used to pretty quickly. So these orbitals will exist in energy levels. So energy levels is still good, but they're going to occupy different waveforms. And what's a waveform? Well, the easiest way to think about it is a wave where we have a particular length to work with, and then we could have these different, well, if you're into music, octaves within that. But it has to fit within a certain wavelength. So we can have these different waveforms within that thing. We also then, in terms of the atom, end up with these different shapes of probability. And then we're going to talk a little bit about that, or in other words, different shapes of orbitals. So You don't need to draw a lot of this. We're not really going to spend much time drawing orbitals, but we are going to hit on a couple. So the s orbital is going to be kind of important to us, and don't draw that. But if you were to figure out the probability of finding an electron and then put a dot for every answer you got, you'd end up with something like this, a big scattering of dots. By the time you're done drawing that, you end up with something that is spherical. It looks round because two-dimensional page, but it's actually spherical like a ball. And then as you go to a different energy level, you end up with an s orbital that is also spherical, so it's kind of similar, but you'll notice it's a little bit different in the sense that there's darker regions and lighter regions, and we'll talk a little bit more about that, but basically the darker it is, the more likely you are to find an electron. We also have a p orbital, and again, don't draw that. If you were to draw anything, these, where you have this double lobe orbital, so each lobe or two lobes represent one orbital, and then I've got three orbitals. And the only difference between those three orbitals is the orientation, the way that they are facing. But they would be exactly the same as each other. They're unique to each other, so an electron in one won't be in the others, but they have this more of a propeller type shape. D orbitals, if you were drawing the P's and the S's, don't draw these. We're not really going to be able to deal with that. But again, a D orbital is a bit more complicated again in that you have these 5 different orientations, different versions of it, where you have 4 lobes in most cases. I know there's the donut, but you've got 4 lobes, and those 4 lobes represent one orbital, and then you've got 5 of those orbitals. And then F orbitals, and we're not going to say anything about those because it gets really weird, and I couldn't draw that, so I would never expect you to. But those are what I mean by the shapes of probability. Only certain wavelengths or energies are allowed. So that's kind of the nice things about in terms of the specific energy levels is it just sort of automatic, because if I look at a wavelength of a certain size or a certain total distance that I can fit my wave into, only certain things are possible. If I take that taller wave and I stretch it out even just a little bit, it no longer fits. It requires more space. Whew. Finally, how do I describe the electron? I'm not going to draw F orbitals. I'm not even going to draw S orbitals all that often. I'm going to write the electrons, or I'm going to describe the electrons in quantum numbers. And we're going to actually have a total of 4 quantum numbers. 3 of them are based on the Schrodinger wave equation. If you're writing stuff down, don't write down the Schrodinger wave equation, because all I'm going to have you ask you to do is sit there and admire it. You're never going to write it. You're never going to solve it. This is it. Okay? That's enough. Right. And solving it is going to require 3 numbers. And I know you can't see where those numbers are because that equation is actually much larger than it looks, but that's not something we're talking about right now. So we're going to talk about all 4 numbers, but the 3 of them are required by the wave equation. We'll talk about how the 4th one fits in. The first one is just we're given the symbol n for the principal quantum number. And it effectively represents the energy level. And it then is, if you were comparing 2 different electrons with different values of n, that's going to be your best way of understanding the energy, mostly. It's kind of like the orbit number where we had the first ring, second ring, third ring, and that was our first, second, and third energy level. Same kind of thing. Lower values of n tend to be a little bit closer to the nucleus, but it doesn't mean that that's the only thing they can do, right? We're not on a fixed orbit, we're not on a fixed ring. We do have these weird shapes, so we can be close to the nucleus all the time, but less likely in a higher value of n. Values are just the counting numbers, 1, 2, 3, 4, and so on. Then we move into L. L is the orbital quantum number. I always write it as a script L just so it doesn't look like a 1, but that's the only reason for it. It's sub-energy level. And sub-energy levels are, well, the shape of the orbital distribution, the shape of the probability distribution. So those s orbitals, p orbitals, d orbitals, f orbitals, those are different values of L. The value of L depends a little bit on the value of n. So for example, for a particular value of n, L values can start at 0, always start at 0 since they can, start at 0 and go up as high as n minus 1. And we'll look at examples of that in a couple of minutes. And then we'll sometimes use letter values. So here I've got L equals 0, 1, 2, 3, but earlier I was talking about S, P, D, and F. And those actually correspond to each other quite well. We'll talk about 1, 2, 3, 4, S, P, D, F in that order. And I know that doesn't seem like much of an order, but it is. Let's leave it at that. Next quantum number is the magnetic quantum number, or M subscript L, which I usually just say M sub L. And that tells us the orientation. Remember we had those 3 p orbitals that were exactly the same, just facing different ways? That was your different values of m sub l. And how many sub-values or how many magnetic quantum numbers values you have, however number of m sub l numbers there are, that tells you the different number of orientations. So we had 1 kind of s orbital, 3 kinds of p orbitals. Those means we're going to have 3 kinds of m sub l values. The values run from negative L all the way up to positive L, and I'll do an example in a minute and it'll make sense. Now the spin quantum number is that 4th number that doesn't fit into the equation, but it ends up becoming the, well, we have the wave equation, but we also have wave-particle duality. So here's the particle side of it, where the particle actually has a spin. Now the other thing is it allows us to do is have electrons pair up, because we've noticed that that happens, so they need to have their own numbers. Values are just negative 1/2 or positive 1/2. Okay, well, how do we use that? What does it look like? So one kind of typical question that kind of you should be able to do at the end of this is, if I were to give you an electron in a particular energy level, so find the quantum numbers for an electron in the 4th energy level, what are the possibilities? Then, well, n is equal to 4, L starts at 0 and moves up as high as 3, m sub l will be all the way from negative 3 all the way up to positive 3, and then m sub s, the spin number, is negative 1/2 and positive 1/2. Now here's what you need to know, and I'm going to say this quick and then we'll get into this in more detail another time, is that that's all the list of possible numbers. So in the 4th energy level you have room for 32 electrons. Just picking different combinations of those numbers, you should be able to get 32 electrons. You're never going to be asked to do all of that, but understand that that list represents just the possible values, not one specific set for one specific electron. There are other kinds of questions that we're going to be doing using these quantum numbers. Here are the list. You don't need to write them down because we'll come across them later. The only thing I want to point out is number 3, that 3 is very, very similar to what we just got finished doing, but it's much, much more specific. So when we get there, we'll have to make sure that we understand what the difference is. And the other one is just sort of understanding types of orbitals versus number of orbitals. Okay. After that, based on where we're at, you're going to be asked to come up with quantum numbers, and eventually you're going to be asked to use them and understand differences between them and things like that. But that's really where we're going to leave it for today. Talk to you another time.